Hey everybody, this is Larry. This is the last day, I think, yeah, of the January Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's farm. Thanks for this journey. Another month down on the books. We have a 1400-day streak going, so I don't even know what that means anymore. What are streaks? Why does it matter? I don't think I care that much about streaks, but it is content, I suppose. Yeah, I hope everyone's having a good January, or well, I guess it doesn't matter anymore. If not, then here's February. And speaking of which, I just kind of came back from another run, but today more of a VO2 max run, so I just got my heart rate up pretty high, which is nice. But also means that I'm pretty tired. I don't know. I feel like every day I've been saying pretty tired on these things, but I've been trying to go all out on the workouts, but the recovery is a little bit tough. But we'll see how that goes. Maybe this allows me to kind of think clearer. Today's problem is 739 daily temperatures. Given the array of integers, temperatures representing the daily temperatures, return an array answer such that answer sub I is the number of days you have to wait after the ith day to get a warmer temperature. If there are no future days for which this is possible, keep answer sub I is equal to 0 instead. Okay. So basically this is saying that for each index, find the next index in which it is bigger, right? Okay, so I mean I think these kind of problems are a little bit tricky because I think the way that people teach it is a little bit silly. Um, and just to be honest, this is how I kind of learned a little bit as well because I learned this kind of thing much later on. Um, I don't even maybe that's not true. I mean, I learned this before there was a term for it. I think that's or like a more weird specific term for it. Because I think back then it was just like a regular quote unquote regular problem, and not really this like funky term, funky pattern that people ask you to remember. And for some reason there are a lot of people who thinks that the best way to kind of learn these things is to memorize some pattern, which look, if you have an interview tomorrow, I guess it is what it is, and you do your best, you know. But if you actually have time and you pace yourself, I always recommend just learning. And that's the other thing is that about these videos, and maybe this is a little bit of a side rant, but like when you're in an interview, you're not getting interviewed at what you understand. I think that's the thing that people I think don't really dig into. I mean, it's very obvious when someone tells you this, right? Like when you're in an interview, you're not getting interviewed for what you understand. You're getting interviewed for what you can do for them, right? I mean, this is very obvious. This is very easy, but for some reason, people kind of watch my videos, and I always in a lot of my videos, I don't. Well, there are two things. One is that I don't make it perfect because I want you to make it perfectly if you want to add verb, because I want you to see how my thought process and my attempts and my things. There are a lot of videos that just shows you the perfect quote unquote solution, and they're like, oh, he sounds so smart because he or she or whatever like reads it off a paper or whatever, right? I mean, and if that's what you need, that's what you need. This is not that kind of channel. But the other thing is that I try to give at least a little bit of concepts, but I don't always connect all the dots easily. Because I do actually, and this is a conscious thing. It's not like I have 3,000 videos by now, right? So like if I want to optimize for that, I would have already, and maybe I would have gotten more views. But that's not what I want to do. I think people who finds the value in what I do will get the value from it, and if they don't, then they'll just find something else. I mean, I have no interest in being the same as everyone else, and I get many requests from people asking me to like, why don't you do this? I'm like, no, you just watch the video that does that. You don't need my video. It's okay. Anyway, and that ties back together because um, one is that you still have to do it, and understanding it is fine. And you see this in a lot of videos that I do sometimes on the contest stuff, especially if I struggled on Q4 or whatever it is, for me, it is not good enough to understand the solution. And it is not even good enough for me to understand the solution and then implement it, right? Like, or if I, no, let's say I didn't get a problem during the contest, I, quote unquote, do a cheat thing and just like look up the solution. It's not enough for me to like, oh, I understand it, and it's not even enough for me to like go, oh, I understand it and I implemented it, so now I must know it, right? Like that's especially when you get to problems of that level, when it's hard enough, when it's difficult enough, and it's not. I would say that it's not memorizable. It's just that there's no use in memorizing because every problem of that difficulty is going to be, slightly different enough that memorization is not that interesting or even useful. For me, it is really, really working hard to really, really work backwards to understand. And a lot of this requires a lot of practice because you have to really know yourself, really know how you operate, and really, like, through thousands of problems of like, okay, historically, and I look at this problem, I do it this way, I do it that way, so I need to kind of add a little bit mental trick to be like, okay, maybe it could be this other thing, or something like that, right? And the way that I do that may not be different. May be different than how someone else does it, right? Like maybe I'm better at dynamic programming. Maybe you're better than me at greedy proofs or something like that, right? Everyone's a little bit different, and that's what I always say. But I think people don't really take it, especially the younger people. It's still a lot of things to learn, so everything is new. So I know that it's hard to prioritize. When everything is new, you could do anything and you'll still be learning. But at a certain point, you have to kind of figure out how to squeeze that little like things at yourself, and also just like working out specific things so that you don't make certain mistakes, right? Like for me, it's not this problem, but you've seen it sometimes where like I go, oh, there's a mod in the problem, so I go mod, and I type out mod because I know, and I still forget it sometimes, right? But that's just like one of those things that I do. And sometimes it works in other ways, like I write certain things in a very specific way, even though it looks a little bit awkward because of like consistency or something like that, so that I'm guarding against my mistakes, my potential mistakes, which may not be your shortcoming, right? You may just be like, why is Larry doing it this so silly? Because anyway, this is a little bit longer rant, but yeah, my point is just that and why does my rent matter for this problem? My rent matter for this problem because this is, I believe, is a mono stack or mono queue maybe. I actually never remember which one it is until I kind of go through it, and I haven't gone through it yet. And the reason why is because I don't like to memorize it, so that's why I'm going through it. I do actually have a video on YouTube, so I think but that one's on monoQ, so it may or may not apply. But the thing that I go through with monoQ is the same thing no matter what. It's just coming up with invariants for a problem, right? And some videos I do go over proving it, and today we'll go over how I think about this problem, and none of it is going to be memorizing. None of it is going to be stack. I mean, sure, if you memorize it, it's going to be faster, or like you could implement it faster. But it only works if someone gives you the exact same problem wherever you go, right? And for me, that's really not, like I'm getting old, and also like my memory is not as good as it used to be. So I don't like memorizing stuff. Which is why I didn't do that poorly. But that's why I struggled with like Orgo or PChem, for those of y'all who took those classes. But all right. Yeah. So basically the idea, and first of all, because we have to do like afterward, like the day after, for me it's easy to kind of think about it from right to left, just like going backwards. I mean, you don't always have to, and sometimes experience will tell you which way is easier. For me, it just for now, I mean, we'll prove it, we'll work for it, but for me, intuitively, it makes sense to go from right to left. And as a result of going from right to left, I'm just going to reverse it real quick. I have to be a little bit careful because with this problem, you're supposed to return the index. And of course, with the index, maybe you don't. I mean, okay, maybe we don't even have to go this way. Maybe this is a little bit confusing, so I don't know. So then you can maybe just count backwards, right? But I always feel like counting backwards looks really ugly in Python. I mean, look at this. This is such a weird looking for loop. Still now I'm like, why? But and the question is, okay, I mean, let me step back a second and say that the obvious solution is n squared, but of course n squared is going to be too slow, or at least it's uninteresting. Given that n is 10 to the 5th, n squared is going to be too slow. So yeah. And the second, so then what can you do? So the idea behind the next step is going to be, well, if we can do O of n each step, there's going to be O of n steps, and you have to look at each number once. So it's going to be some variation of O of n. So you have a loop of O of n, and you're trying to reduce it to the inside loop, either to O of 1 or O of log n. Either one is going to be fast enough, but maybe for interviews or something like that, you might have to do a little bit optimal, or at least do the best you can, right? Yeah, so now, when that happens, we have to do two things, right? One is kind of what I call processing, maybe. No. Okay, maybe there is one processing, and this is just like processing an item for future use, and then the other is, I don't know, usage. That's really weird word, but like solving. So basically, this is just using the pre-processed data structure, whatever it is, to solve for the current item, right? And this actually comes up quite a bit. This kind of idea of breaking it down to like a linear loop of like faster things. At least for the more basic problems, but it's also always it's a good first step to kind of think about, right? And yeah, and then here the idea is that okay, and here as we say, we're going backwards because I don't know, right? How do I do this backwards? I said just type it backwards. Maybe I'm a little bit lazy. Right, so this is just backwards, maybe. Right, so then this is the order we're getting the numbers, and then the first number is 73, right? So what is going to be the answer for 73? And maybe you could kind of do a sentinel or something like that, but the first one is always going to be 0 just because, so yeah. And then the second one is going to be 74, right? So now you have a 74. Well, what happens, right? So the solving step, okay, so right now 73, it floats in this data structure of one item, so it could be anything for now. We don't have to think about it. But then now we have 74 coming in, right? Let me put an arrow here. Oh, I looked at it backwards. Sorry. I reversed it twice in my head. So, okay, so 76 is the next number. Sorry, friends. So now the next number is 76, and then we go, okay, what can we do with 76, right? So 76, we know that we look at all, let's say in an even naive way, in an n squared kind of way, look at the previous numbers. 73 is not going to be big enough, so that answer is going to be 0. Right, but then now look at the future, right? Now we want to add 76 to some data structure that exists with 73. And then the idea here is, well, let's say we're still going forward in this direction, and then now they're really only kind of, so it's given 73 and 76, there are only 3 unique case. I mean, for now I'm not going to do tie breaking or like assuming. For now I'm going to assume the numbers are unique, just to make the cases easier to visualize, but it doesn't have to be. But yeah, and there are three cases, right? There's so for the next number or numbers in the future for some number x, there are three cases. The x is less than 73. X is between 73 and 76. Oops. And then x is greater than 76, right? So x can only be in these three cases, except for, assuming that they're unique. Just because the equal cases are practically the same, but yeah. But okay, right? So then now we can go through it each one by one, right? So let's say x is less than 73, warmer, right? So yeah. So let's say x is less than 73, what happens? Well, what is the answer if x comes in here and it is less than 73? Well, then the answer is 76, right? And then here, what is the answer? Also 76, right? And then here, what is the answer? Well, the answer is 0, but yeah, because it is greater than 76. But here you can kind of see that, oh, wow. 73 can never be the answer for any number in the future. So why don't we just remove it, right? That's basically the idea. And then, so then here, when we process the 76 and we process everything for future use, we go, okay, it's actually impossible for 73 to be the answer. So then let's just keep 76. Okay. And then now the next number is 72. Right? And 72, we have the same thing, except for, okay. Okay, 72, the answer is 76, as we said before, because 76 is the next number. We should keep track of the index and stuff like that, but we'll worry about it in the actual coding. So 72, right? And then now, again, we have a few cases, right? So we have x is less than 72, 72, 76, right? And then x is less than or greater than 76. And then here, what's the answer? Well, actually, the answer is 72, right? What is this answer? The answer is 76. And this answer is 0. Or, negative 1. This is 0 in this case, which is actually awkward. But let's say negative 1, right? Yeah, so that means that 72 should belong here. And 76 should also belong here. Because both of them has a possible answer, depending on what the future is. And then, okay, so now we go again, 69. All right. Yeah, so 69, we look and the number that we care about is 72. So then here, the next number, the biggest is 72. And again, here are 4 cases, really. And this may be the last one that I do. I'll do one more after this because I think you'll see in a second. But yeah. And then here, for example, what's the answer? Well, it's 69. Here, the answer is 72. Here, the answer is 76. And then here, the answer is, again, 0, right? So that means that every number can be a possible answer. So we do that. Another thing to note is that we actually don't even need to draw the 76, right? Because we know from previous, like the loop invariant, or just like, it's not quite induction, but just like we already proved that in the past. Like if you actually, I mean, I know that I deleted the ranges, but if you had kept the ranges as, just this, right? You can think about what we hear, just adding to it, right? So we don't have to actually iterate through 76 again to kind of check whether it can be possible, because we know it's possible because here all we do is split this range up to 72, right? Or 69, sorry. And then, okay, so then the last one is 71. So 71, we kind of look through the answer and we say, oh, 72 is the answer. That's fine. And then maybe another way to visualize this is that, okay, let's split this up. Like, let's look at this and split it up, right? So we could actually split this up to 71, right? And the answer is going to be 71. I know that we only do whole numbers, but just bear with me, I suppose. And the answer is 72, right? So then now we notice that 71 here, and we have all these things, and it's good. But one thing to realize is that, oh, wait, in this case, is this still true? And the answer is no, because if you have a smaller number than 71, we could remove 69. And it turns out that, yeah. So now this is your table, if you will. And that's basically the idea, right? You kind of just remove things that are not possible. And you kind of see that when you have a 71 here, when you have a number that's bigger than a previous possible number, well, that number is just not possible anymore, because in the future, you can't look up this lookup table and be like, oh, it's just not possible, because 71 would kind of, it's a superset of those smaller number, right? And that's basically the idea behind this problem. And the other thing to note is that, and that's it, right? And you can implement this kind of for a stack by going backwards, and so you don't have to look at everything in the past. That's one. That's just like realizing the data structure to kind of keep it, because you only look at, if you look at these intervals, you look at it from the top down, one at a time, to kind of, remove them as necessary. So that's one. So you use a stack, right? The other thing is that, note that I never had to say anything about monotonic. I never say anything about decreasing. I never say anything about that. It doesn't matter, right? At least for this problem. The only reason why people kind of use this as shorthand is that if you kind of look at this, it is an emergent property, right? It is not an actual thing that you have to know about it. It is just something that, oh, it happens to be decreasing. And I actually, before we kind of step this through, I actually would not remember whether it's increasing or decreasing, because I don't know. It doesn't I'm sure there are people who go, oh, you have to get the next higher number, so of course it's decreasing. For me, that is useless to remember. I mean, it's not useless to remember, but it's trivia to remember, right? Not trivial, but trivia. I don't know, remembering Abraham Lincoln's birthday, right? I don't know, it's trivia. It's fine, it's okay. I'm not going to hate on you for remembering or knowing, but I don't care, right? It's not important to me. Actually, I have no idea what Abe Lincoln's birthday is, or whatever it is, right? Your favorite president, or whatever, right? I don't know. So it doesn't matter. Just like this doesn't matter for this particular problem, right? So this is, and here, this is where people go, oh, we use a stack for this. So we use a stack for this, and it's monotonically decreasing, so let's call it a monostack. And that's how people kind of start calling things out. These problems are monostack. But really, it is just an invariant of how we devise our algorithm from scratch, and how we kind of think about these problems to be like, oh, this is how we figure it out. And I don't know. I don't know how, to be honest, like I said, I don't know how or why, other than that, I guess it makes it easier for people to remember and quote unquote recognize patterns. But if you actually work on your problem solving skills, I don't know. I don't know any reason why you would kind of just memorize the mono stack as a thing. I mean, I'm sure if you've done these enough times, then maybe you'll remember it. But remembering things is not the same as memorizing things, right? As a strategy. So I don't know. But yeah. Okay, so let's kind of get started, right? And then stack, and maybe we can actually I'll do a infinity thing just as a sentinel, and that'll be the second is usually the index. So then here it's a little, I think it doesn't fit this quite exactly. But here we have to figure out the invariance, right? And the invariant now is that, given a new number, we have to kind of look through this table and then remove things that are not possible. For example, if, and this doesn't match this, I guess it actually does, 75, we get 75, then this thing can no longer be possible. So then we remove it, right? And then this also no longer be possible or is overlapped, so we remove it. And then, right? So something like that. So yeah. So here we go, while length of stack is greater than 0, and it should, I know this is actually not necessary because we have the sentinel, but whatever. Stack of -1 of 0. If this value is less than or equal to. So the idea here, I didn't go over this because I just wanted to make sure that is just keep it simple for now. But the reason why I have equal to here, and how you think about this equal or not equal is that if you have two numbers that are the same, let's say let's say we have this stack and then we have another 75, right? Let's say 75 in a row. So then now this is what our stack looks like, and we're given a 75, right? Then what happens? Well, the question is whether the old 75 is possible, right? The old 75 in this case is not possible because you would just want the closer 75, and because the older, farther away 75 is not possible, we would just remove it. So that's basically the idea. And here, that means that's how I think about this equal sign or less than equal as part of the removal. And so then we pop, right? And then yeah, answer sub I is equal to the top of the stacks, number 1 for index, and then we can append temperature sub I and then I, right? And that's pretty much it. Oops, that's like answer. Whoops, did I mess something up? I mean, clearly I did, but the top of the stack. This is embarrassing after I kind of did the whole spiel. Did I misunderstand this? Oh, it's the number of days waiting. Okay, sorry. Okay. I mean, that's fine. I just kind of misread the problem. This is actually pretty straightforward. I mean, straightforward to fix because now the answer is not, because I had the index, so the number of days is just the current index, or well, I guess minus I, and that's it, right? Oh, except for 0. So, yeah, because I had the sentinel, so because I expected it to be well, I just thought it was the index, and I thought you're supposed to return 0, so that's why. Okay, so then now maybe we can just write like, I don't know, maybe I'm lazy. Maybe there's a good sentinel, but with this 0, we do I00, else we do this. Right? I mean, easy fixes, it's just, I misread the problem, right? So yeah, let's give it a submit. And that's pretty much it, right? Like I said, I think the problem that I probably actually did the same. Oh, why is it so much slower? That is very awkward. But yeah, this is linear time. This is all one amortized. Even though there's a while loop here, keeping in mind that we only, for each item that we get as part of the input, we only push and pop once. So that means that each item can only be push and pop once. So in total, it's going to be linear. So this is linear time, linear space, and that's what I have for this one. Note that, I mean, if I said this a few times, and I want to put emphasis on it, is because, like, listen, I've never said anything about monostack except for tell you not to think about it as monostack. So you really don't need that. And I think, I know people could kind of be like, oh, let me like work a few monostack problems to get the feel. And it's really not necessary. It's just about like this idea of like figuring out the invariance of the loop invariant, and then like try to figure out like these if statements and then working through backwards. But yeah, that's all I have for this one. End of the month. I'll do a premium problem after this, even though this was a long explanation. But yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.